I want to talk about some recent work that I did with Pengui Yao on constructing pseudorandom generators for positive spectrahedron. Right, so first things first, let me tell you that this talk is going to be pretty classical, or in fact, very classical. So most of the things I'm going to talk about are classical TCS. I'll be using the word quantum twice in my talk, but just because I want to use the word quantum, I'm using it. It's not because like it has any quantum relevance. Right, so yeah, another thing is like, so the reason I got with this collaboration is because Pengui was a postdoc with Ronald when I was his PhD student. So like I know Pengui for quite a while, and last year we met at Simon's and we started collaborating on this thing. Right, so let me begin, and let me start with telling you what's okay, well, what are linear programs? So what's a linear program? It's just like you're optimizing a linear function, and not just you're optimizing a linear function, you're optimizing it over a geometric object, and this geometric object you're optimizing over is called a polytope. Right, and I will describe what a polytope is in a bit. But let me first tell you what a linear program is more mathematically. So it's just defined by it's just defined by k constraints, defined by w1 to wk, and another cost function c. All these are vectors in Rn. And the goal is you're going to maximize this linear function c transpose x, subject to a bunch of k constraints. And these k constraints are the inner product between w1 and x is at most theta 1, and so on and so forth, up to inner product between wk and x is at most theta k. So the set of all x's that satisfy these k equations and that maximize this is going to be the is called opt, or the optimum value of your linear program. Right, and I'm sure everybody has seen linear programs, like this is like used everywhere in all fields and stuff like that. And the reason this is so interesting and used by everybody is because it's efficiently solvable. So it's polynomial time. You can compute opt, or even approximations of opt, in time polynomial in k and n, and even like error parameters and so on and so forth. Right, so that's what is exciting about linear programs. But let me tell you some geometric intuition as to what's going on. Like more like I want to cover like what's a polytope. So before I talk about polytopes, let me first talk of what's a half space. So what's a half space? Just think of R3 for now, this cube right now. And I'm just going to cut this cube in by this orange slice, and the top of it is going to be labeled 1 and the bottom of it is labeled 2. Those of you familiar with machine learning, this is like a support vector machine where you're cutting the space and you're hoping to label things plus or minus 1. Right, so half space is just a constraint in Rn that divides the space in some sense. So it's just a function that takes Rn, the set of points in Rn, and it maps it to either 0 or 1. Here, for example, is it to the left of this orange slice or to the right of this orange slice? That's it. And if you have to be slightly more rigorous, what this says is a half space is defined by a vector w in Rn. And I'm going to be defining, most of the stuff I'm going to be defining here is over the Boolean cube, or minus 1, 1 to the n. And we say the half space evaluates to 1 if the inner product between w and x is at most theta. And it's 0 otherwise. So another way to write this is just the half space is just the indicator of this function. If wx is less than theta, or the inner product between w and x, where this inner product is over R, is inner product between w and x is at most theta, then this function evaluates to 1. If the inner product between w and x is strictly greater than theta, it's 0. So that's a half space. Right, and right. So the next step, I'm going to be looking at a generalization of a half space. That's called a polytope.
Sorry, Srinivasan, could you repeat the previous bullet? I have trouble parsing what it says there.
Right, so h1 of x is just a function that maps like the Boolean strings to 0 or 1. And it maps the Boolean string x to 1 if the inner product between w and x is at most theta.
So you're defining a Boolean function h1 in this line.
Exactly. That's what I mean by half space here. Exactly.
Okay, thanks.
Right. So what's a polytope? It's just an intersection of half spaces. So think of like this orange thing, just cut the space into 2, left or right. I can put in one more constraint. Maybe I put in one more constraint and I want, so like the top thing is one half space. This is another half space. Thing looking at you is another half space. So I can look at an intersection of half spaces. So the set of all x's that satisfy all half spaces, that is called a polytope. And if I have to be slightly more rigorous, I have these vectors w1 to wk, all in Rn, like on the top of the slide. And a k-facet polytope, that is, it's an intersection of k half spaces, is just defined as the set P as a set of all x's that satisfy all these half spaces. So this is just a logical AND here. So h1 of x is all the x's that are such that w1 x is at most theta 1. H2 of x is all the x's for which W2x is at most theta 2, and all the way Hk of x are the set of all x's for which Wkx is at most theta k. So this is a polytope. So again, so it's just a generalization of half space. So half space just cuts the space into two. Polytope kind of looks at a bunch of half spaces, and you want to make sure the x's satisfy all these half spaces together. And if you want, you can write now x, or the opt of a linear program, as just the maximizing of a linear function where the x's sit inside a polytope. So that's what I mean. You're optimizing a linear function over a polytope. All the x's that lie in a polytope, you're maximizing a linear function over it. Right. So this unfortunate part. Right. Yeah. Okay. Fine. I can just say it in words. So there are lots of applications of linear programs, for example, in optimization, combinatorics, like geometric analysis, like all areas of theoretical computer science. You can find linear programs appearing. Right. But the main motivation of this talk is I'm going to be looking at something more general, a generalization of linear programs that are called semidefinite programs. So what's a semidefinite program? So earlier in my previous slide, this W1 to Wk were just vectors in Rn, but now I'm going to let, oh, sorry, before that, it's still you're optimizing a linear function, but not only are optimizing a linear function like in the previous slide, you're optimizing it over a larger space. So earlier you were optimizing a linear function over a polytope, but you're now optimizing a linear function over a larger space called a spectrahedron. I will again tell you what a spectrahedron is in a bit. Right, so as I said in the previous slide, all these W1 to Wk's were all vectors in Rn, but now in an SDP or semidefinite program, these W1 to Wk are going to be symmetric matrices in Rn. So they're n by n symmetric matrices. Right, so what's a semidefinite program? So in semidefinite program, again, opt is the optimum value of this SDP, where you're maximizing a linear function, C transpose X, subject to a matrix valued constraint. So X1, W1, all the way to Xn, Wn. So the left-hand side is just a matrix, and you want it to be at most D. And this at most is called the lower ordering. And what it means is we say C is at most D, or two matrices C is at most D in the lower ordering if D minus C is positive semidefinite, or all the eigenvalues of D minus C are greater than 0. Sorry, are non-negative. Right, so this is a semidefinite program where you're still maximizing a linear function, but subject to a matrix constraint. Right, so for those of you who are not so familiar with SDPs and it's not super clear why this is a generalization of linear programs, one way to view that immediately is just you can think of all these Wi's and W1 to Wk as just being diagonal matrices. So if W1 to Wk is just diagonal matrices, and if you just stare at this for a second, you can just write down the opt here as this. And now if you look at this, this is exactly a linear program. So an SDP is just a linear program where the constraints are not just linear function, are just like linear functional over matrices. That's about it. And if you restrict the matrices to be diagonal, you get back a linear program. But of course, here it could be arbitrary symmetric matrices, and that's where the power of SDPs come in. And of course, the natural question is, okay, sure, this is a generalization of a linear program. Is it still efficiently solvable? And it is. Right, so before I tell you some properties about SDPs, maybe I can tell you what the spectrahedron objects look like. So what is a feasible region of this optimization program? And that's where spectrahedrons look very complicated. Like it could contain an elliptope, it could contain a cylinder, and this weird object. I don't know what this object is, but I saw a famous person giving a talk and saying this is a spectrahedron, so I trust him. So yeah, so spectrahedron could be a funky object. Like it could be pretty weird because it's defined. It could contain like polynomials inside them. It could contain matrix constraints inside them. So these are pretty wild objects in some sense. And as I said, SDPs generalize linear programs, and not only that, they are still efficiently solvable in K, N, and the error parameters. So that's exciting. Not only can you generalize linear programs to SDPs, but they still remain polynomial time solvable.
Sorry, question.
Yeah.
A spectrahedron is a convex set, isn't it?
Yes, it is. And this,
your middle picture doesn't seem very convex. I
agree with you. I think there are some shadows in here and there, which I'm not able to see right now.
I see.
But you're right. Right. So yeah. So SDPs generalize linear programs, and they are still efficiently solvable. But unfortunately, as I said, because these objects are so complicated to even like describe, they're not very well understood. Like several basic properties of spectrahedron are still not well understood. And I will come to this. This is going to be important for us, and I will come to it in a few slides. But these things have found applications everywhere. Like, for example, like if you want to approximate max cut, the best thing that the 0.878 by Gomez-Williamson is through an SDP. Then in the SOS hierarchy, and even in quantum computing, for example, just proving QIP equal to P space, that involves like writing it as an interactive proof as a semi-definite program and so on. So like SDPs have appeared all over the place, and they're as exciting as linear programs, even in all areas of theoretical computer science. Good. Also, if anybody has questions, you should just stop me there and ask me. Like right now, it's just introduction, but things are going to get slightly more technical. You should just stop me immediately and ask me. So next slide, I'm going to get to the other part of the talk. So like the first two slides are just about geometric objects. The next slide is going to be about pseudo-random generators. And eventually I'll put them together in a couple of slides. So what's a PRG or a pseudo-random generator? It's just a function, and a function that expands randomness. So like you give it like small number of random bits and it produces you a lot more random bits. So for example, here a PRG just takes like pristine gold coins R pristine gold coins, and it's going to give you n fake silver coins. And the reason why this is exciting is in some sense because no algorithm should be able to distinguish whether you give it n fake silver coins or n true silver coins. So that's what a PRG is informally. It takes small number of good random bits and produces large number of fake random bits. So that's why it's called pseudo-random. To be slightly more rigorous, we say a PRG for a class of functions is just, so think of script C as a class of functions. It maps n bits to 1 bit. And we say this class of functions is fooled by a PRG G. So again, G is a function that takes R pristine bits and produce n pseudo-random bits. So that no function in my function class should be able to distinguish whether I got pseudo-random bits or truly random bits. So I could pick a uniformly random arbit string and apply the function G to this uniformly random arbit string, or produce n pseudo-random bits. No function in my function class should be able to tell you whether I got uniformly random n-bit string or a pseudo-random n-bit string. So that's what a PRG is, and this should hold, so this function should fool all functions in my concept class. And of course, like there's one trivial PRG that we all can think about, just fix R to be n. So if I fix R to be n and G to be the identity map, then this quantity on the LHS is just 0, because like F applied to the uniform input and again F applied to the uniform input, both are equal, this expectation value, so it's 0. And that's where the concept of seed length comes in. So the seed length of a PRG is the number of, it's kind of like the expansion property in some sense. Like ideally you would like R to be as small as possible, N to be as large as possible. And this R is quantified as the seed length of a PRG. And ideally, in a perfect world, you would like PRGs for all classes of functions where the length of the seed is only polylog in the parameters of your concept class. So you would like, for example, let's say your concept class just depends on little n for the time being. You would like a PRG such that the seed length is only log n, and using just polylog n bits, I can produce n bits of randomness. And if you could do that, that's very exciting. And I'll tell you why in the next slide. But PRGs, again, have found their applications all over in theoretical computer science, even in quantum computing. So like it's a very vast and interesting concept that people have been using for various topics. Right, so again, as I said, like this is the definition of PRG, and really the goal is to have a seed length for a PRG for an interesting concept class that's polylog in the input parameters. Right, and one of the holy grails, I mean, the holy grail is to construct unconditional PRGs, because that would imply P is not equal to NP, but maybe that's out of reach, or I don't know what the status of that is. But something that people are interested a lot in these days is constructing PRGs against the class of polynomial size circuits unconditionally. And if you could do this, that implies BPP is equal to P, and which is already a very interesting, which is already a breakthrough. Like it says like you can de-randomize all randomized algorithms if you had a PRG against all polynomial size circuits unconditionally. But again, this is a hard problem. People are still, I don't know what the status of this problem is, but we're still very far away from proving this. But something other people are interested in is like, can we slowly build up to solving this holy grail? And in that direction, what are interesting circuit classes? So like, for example, like, can we fool a smaller class of circuits unconditionally? And there's been a lot of work. Like there's one read-once branching program, CNFs, AC0, read-once formulas, and so on. So a lot of interesting small circuit classes we can fool unconditionally, but to fool the class of all polynomial size circuits, we don't know how to do that yet. Right, and another direction that's kind of like spin-off of this in some sense is like, can we not only fool like interesting circuit classes, can we fool kind of functions? Like, for example, like you could look at, for example, let's just say a function is defined by a polytope. We know polytope is solvable in a polynomial time. So maybe can we fool even geometric objects like say polytopes? And in this direction, there have been lots of works. I'm going to summarize all these works in the next slide, where they look at constructing PRGs or pseudorandom generators for geometric objects. And ideally, you would like it to be the seed length to be polylog in all the parameters of your geometric object, say the number of facets, number of variables, so on and so forth. Right, so this has again been a rich area of study, and I can tell you a quick sketch of like the works. Like most of what I'm going to be talking about for the rest of the talk builds upon research in the third direction here. And before that, let me first sketch you what was known before our work. So the first thing was this, in my opinion, a breakthrough work of Meka and Zuckerman back in 2009, and that was also done by Diakonikolas and others, where they constructed pseudorandom generators for half spaces. So recall what was a half space? It's just like you have a space, Rn, and I want to cut it by a half space, and that just says what's the left of the space is 1, what's the right of space is -1. That's a function. And I want to fool the class of all half spaces. And Meka-Zuckerman, they gave this beautiful technique based on invariance principles to fool half spaces. I'll talk a lot about this Meka-Zuckerman work in a couple of slides. And right now, people have looked at this a lot. And finally, I think in 2015, this work by Gopalan, Kane, and Meka, they have PRGs for half spaces that has seed length that's polylog in all the parameters that you would care about. Right. And then like following this up, this line of work, there's this other line of work for fooling polytopes. So this was started by Harsha, Clemens, and Meka in 2013, where they said, if you can fool half spaces, why not just fool an intersection of half spaces? But of course, the hard work is in proving that you'd like to fool a polytope or an intersection of half spaces with seed length that's again polylog in all the input parameters. That's where the hard work is. But they managed to get it for a certain class of polytopes. And finally, like a couple of years back, Ryan O'Donnell, Rocco Servedio, and Liam Tan, they gave optimal PRGs for polytopes with the seed length that's polylogarithmic in almost all parameters, but not all parameters. Right. So this has been two competing lines of work. And there's another generalization, which I haven't spoken about so far. It's called about fooling polynomial threshold functions. So what's a half space? A half space is just an inner product between a vector W and X. So that's a degree 1 polynomial. But let's just say I have a degree 2 polynomial in X1 to Xn. So P is a degree 2 polynomial. And I just say, for example, is it to the top of this polynomial or to the bottom of this polynomial? So that's what the sign means here. So for example, these are cubic polynomials. Oh, I don't know about this, but it's a cubic polynomial. And you ask whether it's to the top of this polynomial to the bottom of this polynomial. That's a Boolean function. Can I fool such functions that are defined as polynomial through polynomials? Again, this work of Meka-Zuckerman could be used to fool PTFs. And then like between 2010 to 2013, like Daniel Ken went crazy. He proved like many structural results about PTFs. And I think the best PTFs we have right now are through Daniel Ken. But like last year, there was a significant improvement to constructing PRGs for PTFs by Ryan O'Donnell, Rocco Servedio, and Liam Tan. It's a different paper from this, but this only works in the Gaussian space, not in the Boolean space. In the Boolean space, I think the state of the art is by Daniel Ken.
So when you say PTS, do I understand correctly? So you say PTS, is that polynomial threshold function?
Yes.
Okay.
Sorry, I wasn't clear. So yeah, PTF is just a polynomial threshold function. That's
PTF,
right.
Okay.
Yes.
Thanks.
So what do you mean by the Gaussian setting instead of the Boolean setting?
So when I said earlier, like for example, like, okay, you have a PRG that takes R Boolean input bits and produce n random Boolean output bits. So you would like to fool a uniformly random fake n-bit string from a uniformly random n-bit string. But instead of fooling a fake n-bit string from a uniformly random n-bit string, let's just say I can fool it only against Gaussian bit strings, not Gaussian strings. Then I'm not able to fool it perfectly, but I'm able to fool it against just Gaussian bit strings. I'll come to this in a bit again. So I'm comparing kind of like apples and oranges, like n-bit strings versus n-bit strings would be lovely. Fake n-bit strings with true n-bit strings. But instead, I can only compare like fake n-bit strings with just Gaussian strings.
And
so
this makes sense because it's for geometric objects. Like this wouldn't make sense for circuits, right?
No, you're absolutely right.
Okay.
This all makes
then
sense
I
only for
understand.
geometry. Yes,
Thanks.
exactly. I will come to this again in a few slides again. Right, and the main motivation for our work is a spectrahedra. If you think about it, it actually generalizes half space and polytopes and PTFs. So generalizing PTF should not be immediate, but there are some results saying that all polynomials can be written as semidefinite programs, and there's this connection going on between PTFs and spectrahedron. So in some sense, spectrahedron generalizes half space, polytopes, and PTFs in one framework. And the question we ask is, can we construct PRGs for spectrahedron? And that's really the motivation for this work. Right. So let me tell you like a 1-minute history of how we came to this problem. So like last year when we were at Simons, like Pengui and I looked at this paper of Ryan, Rocco, and Liang, and we thought like, okay, this should be generalizable to spectrahedron, because then there was this rage about quantum computing helping semidefinite programs. But the first thing is like, why didn't these classical people do it already? Like these guys are all very super smart. They're much smarter than us. Why didn't they do it already? So we spoke to a couple of them, and they told us that it's just like there are matrices involved. Maybe there are some structural properties that are just too hard to prove for matrices and so on. And now I'll plug in a code that Aram Harrow told us a long time back. Like classical people are much smarter than quantum people, but it's just that quantum people are not scared of matrices. So really that was the motivation for us. Like maybe these people were not ready to handle matrices in some sense, but we thought like maybe quantumly we have matrix friendly, so maybe we can handle such things. And that's how we prove at least some results in this direction. Like we're very far away from constructing optimal PRGs for spectrahedrons, but we have at least some results in this direction. And that's going to be my next slide. What's the main results? Again, recall this is a spectrahedron, so it's just a set of all Boolean strings, -1, 1 to the n, such that xi, summation xi ai is at most p in the loner ordering sense. And I'm not going to be constructing PRGs for all spectrahedrons, but only for some spectrahedrons. And the spectrahedron I'm going to be looking at is firstly positive SDP spectrahedron. What I mean by that is all these AIs and Bs are positive semidefinite. So in the definition with semidefinite programming, AIs and Bs could be arbitrary symmetric matrices, but I'm going to enforce that these are all PSD because I can make my result only work in the setting. The next thing, which is a fair assumption, is all these AIs are kind of, we have some bound of them. Like we call this like bounded width. That just means the summation AI square are all at most m times identity. So it's not like an arbitrary large matrix and so on and so forth. And the final thing we need is regularity. And right, this is, I think, a strong property that we require, but we don't know how to get rid of it. So all these AIs are kind of like smooth. So like we don't want like some AIs to be extremely tiny in eigenvalue and some AIs to be extremely large in eigenvalue. There should be some sort of like eigenregularity, which is used a lot in this area, like in some sense. And in this direction, this is our main result.
Sorry, can I ask a question?
Yes.
Usually a spectrahedron is a set of PSD matrices, but here you seem to take it as a set of Boolean strings.
So there is you can write it in terms of duality actually. So there is a way to write an arbitrary spectrahedron in terms of set of all x and Rn for which this constraint is satisfied. You can look at, okay, every spectrahedron can be written as a linear matrix constraint by writing the dual of a standard SDP.
But would a spectrahedron be a set of PSD matrices in that case?
In the first case, yes, but in the second case, all the feasible x's in this, so all the xi AI for which this constraint is satisfied, those xi AIs are going to be what is my feasible matrix in your definition.
Yeah, I understand your definition. It's just a very unusual use of the word spectrahedron. But
as far as I know, like
this is how you want to use it, that's fine, of course.
Yeah, sure, but the point is these two definitions are equivalent. There is a way to like write down the dual of a standard SDP, which is a bunch of matrices, and you can write it as a linear matrix constraint as well. Like we discussed this in the paper, like, but I can tell you this more after the talk, maybe. Right. So this is our main result, and our main result. Also, one reason why we chose this linear matrix definition instead of the standard feasible set of matrices is because like it makes sense to not think of it as like a Boolean function in some sense, and you can fool a Boolean function. Right. So what's a PRG grid? Right. So the main result is that we construct a PRG that takes R random bits and produces R perfectly random bits and N pseudo-random bits. And this fools the class of all spectrahedron, and the seed length that we have is log N, which is nice. log k even, which is also nice, but it's not so great in terms of m and 1 over delta, where m is the width of the semi-definite program and delta is like the parameter with which you have to fool the spectrahedron. So our main result is, let's just say you have an algorithm and you give it either a uniformly random n-bit string or a fake n-bit string. It should not be able to tell you the difference between whether the uniformly random n-bit string was lying in the spectrahedron or the fake n-bit string was lying in the spectrahedron. And as I said, like one of the important things of constructing PRGs is you would like the seed length to be poly-logarithmic in all your important parameters. Here we got it to work for n and k, but we don't have it to be polylog in the other parameters, but this is what we have. And yeah, of course, like we can only prove it with positive spectrahedron. But yeah, this is the main result that we have. Right, and right, the main result, since I'm not going to be having too much time, I'm going to be the one technical thing that I'm going to be talking a lot about is called invariance principle for spectrahedra. This is going to be like, I think this covers like the most of the technical meat of our paper, but yeah, so I hope people get something out of just this one technical aspect of our work. Right, and there are other applications of our work, for example, like in learning theory, and we talk about like, for example, like what is like even like basic things like what is the average sensitivity of a spectrahedron, what's the noise sensitivity of a spectrahedron, were all not known prior to our work. We have all these results in our paper, like I wouldn't have time to talk about this. Right, so let me start talking about this technical result, and before that, if anybody has any questions, you should stop me and ask me, or otherwise I'm just going to carry on.
Small question. There's a theta in your assumptions, namely in the regularity condition, that doesn't appear anywhere in the bounds of the theorem. What's happening there?
Oh, you mean tau, right?
Sorry, yeah, tau. Sorry, tau.
Good question. Yeah, you caught something. So the point is, our results, which also works. So the way I would put it is the following: we don't have a result for every tau. We have it for all tau that scales like that's at most 1 over log k times 1 over log n. So like, you require eigenregularity, which is at most a 1 over log k times 1 over log n. It doesn't work for every tau. So this tau, you can think of it as depending on k and n. So like once you fix n and k, which is the parameters of a spectrahedron, you require all the AIs to be at most 1 over log k times 1 over log n times identity, and then our result kicks in. Yeah, that's a good point, but yeah. Good. So let me first tell you what's an invariance principle. And yeah, and more than that, I'll tell you what, again, like I really like this work of Meka and Zuckerman back in 2009, where they said how to construct PRGs based on just this concept of invariance principles. So really, that's their punchline. If you give me an invariance principle, I can construct a PRG for you. So let me tell you what an invariance principle is in the first place. Right. So to understand an invariance principle is just a generalization of the Berriesian theorem. But what is the Berriesian theorem? It's a generalization of the central limit theorem. So what is the central limit theorem saying? So what the central limit theorem says is if you have a bunch of like n random variables, mean 0, variance 1, it says like if you take a sum of all these x1 to xn, renormalize it by square root of n, it converges to the Gaussian. So this is the central limit theorem. But one thing that's not clear in this arrow here is what is this convergence like? Like, for example, does n equal to 1 already converge to G, or how does this, what is this, like, let's just say I want the difference between these two things to be at most epsilon. How large should I let n be? And that's where the Berriesian theorem comes in. So what the Berriesian theorem tells you, it just talks about the convergence of the central limit theorem. It says that for every u, which is a real number, if I want these two probabilities to be very close to one another, that is, I want both the left-hand side to be at most u and the Gaussian also to be at most u, I can bound the difference of these probabilities to be very tiny. So you can forget C for the time being. I just put in here because to be rigorous, but essentially it tells you what is the convergence of central limit theorem. Through, you can understand that using the Berriesian theorem. Right, and so essentially, yeah, and so this thing was proven using this Lindeberg method in, okay, this is not 2022, this is 1922. So I'm not stating a future result here. So, right, so the idea of proving this, which is going to be important, I'm going to be talking about it again in a couple of slides, is it's called using the hybrid method, which is again well known, for example, in crypto and so on, where I'm going to be replacing 1 by 1 x1 by g1 and then x2 by g2, and then I replace 1 by 1 all these x1 to xn by g1 to gn. At that point, it's just a Gaussian. So that's called the hybrid method. And again, I'll talk about this in a lot more detail in a few slides. But really, the punchline of invariance principles is sometimes understanding things in the Gaussian space is much more easier and nicer than understanding things in the Boolean space. And the central limit here, sorry, the invariance principle allows you to translate technical results in like Boolean space to technical results in the Gaussian space. And if you can prove some result in the Gaussian space, that's maybe good enough to translate it back to the Boolean space. It's kind of like the moral picture of what's going on in invariance principles. So the expectation of an object in the Boolean space is very similar to the expectation of an object in the Gaussian space. And so like, how did Meka-Zuckerman use this result first in their first result? So again, recall this is a half space. You're just dividing Rn using a linear half space. So recall this is a half space. So like summation Wi xi is at most theta. And what they observed is something that's kind of like obvious in foresight. So like they observed that if all these W's are smooth, what I mean by smooth just is say the L2 norm of W is close to 1 or the L4 norm is close to the L2 norm, then summation Wi xi just converges to a Gaussian. That's it. And really, if you look at their proof, this is really the crux. Just this observation, along with some other geometric properties, they go to construct pseudorandom generators for half spaces. And the next result of Harsha, Clemens, Meka, they said, okay, fine, if you can do this for half spaces, you can also, of course, do it for polytopes. And recall, what's a polytope? A polytope is just a half space, but you have k half spaces, you're putting them all together, and you're getting, you have k half spaces, you're putting them together, and you like all the x's that satisfy all these k half spaces. So that's a polytope. And what they said is if all these W1 to Wk are smooth, so in Meka-Zuckerman, they just need one W to be smooth. For polytope, they require everything to be smooth. They said if you take this inner product between W1 and X, W2 and X, so recall there are KW, so the K rows and N columns. And if you take this inner product, it actually converges to a Gaussian. So this expectation of Wx for a uniformly random X is close to a Gaussian on K bits.
Srini?
Yeah.
I'm a little bit lost. So what are you showing here?
I'm just trying to tell you how the invariance principle has been used so far. Like all I want to say is like a half space for uniformly random bits converges to a Gaussian. A polytope on uniformly random bits actually just converges to a Gaussian. So if I take the inner product between a matrix W and a uniformly random vector X, that is very similar to just analyzing a bunch of K Gaussians. That's it.
But then
I'm
how
not
is
saying
it
something very deep here so far. I'm just saying like inner product between W and X converges to a Gaussian, and like the matrix product between W and X converges to a Gaussian. That's it. Maybe the next slide will become clear when I try to actually explain why I'm talking about this. Maybe after next slide you should stop me. Yeah.
Because the goal is that you want to show that you want to now do the analysis with respect to the Gaussian, and then include something about the half space.
Yeah. It's more like you want to do analysis in the Gaussians, which is nicer. I'll come to it in the next slide, and that's where people have used this result so far. And
then this other theorem says that the error is something like square root of 1 over square root of n or something.
Exactly. So that's very crucial again. And you're kind of, that's it. I'll talk about Harsha, Clemens, Meka in the next. I'll give you a complete proof sketch of what they do.
And what do you mean by smooth?
Yeah. So all I mean by smooth is, let's just say, for example, all these WIs, they have say L2 norm at most some. So if you recall, like Ronald pointed out, where am I using the fact that these AIs have like largest eigenvalue at most tau? When I mean smooth here, I mean all these W's have L2 norm at most tau. Like they could not be like just the indicator function of E1. They should all have like smooth. It should all be smooth. Like all these WI should be kind of like close to 1 over root 10, for example. One of them could not be 1, rest of them could not be 1 over root 10. Like that kind of property should not
norm, right? Srinivasan, L4 or L infinity norm should be small. Not the
correct. So technically smooth means the L4 norm should be at most the L2 norm times some constant. There's another version of smooth where you just require the L2 norm to be small in the first place. Or L2 norm being smooth is sufficient. So okay, the takeaway is the following. All these W's, the coefficient of these W's should all be very close to one another. Nothing can be super large and the rest of them could be super small. That's really all they require. Good. And yeah, I mean, like removing the smoothness condition was a big open question back in 2013. There have been like sequence of works after that. And finally, it was removed in OST, this result by O'Donnell, Servedio and Tan in 2019. Right, so let me tell you how they established this thing, this invariance principle. And right, so let me sketch you quickly what this Harsha, Clemens, Meka result is. It's very pretty, I think. So recall, this is a half space. It's just like taking a matrix, multiplying it by x, you're going to get a vector theta. It should be at most theta. Right, so what do they mean by establishing invariance principle? Right, so here I'm going to, for the time being, I'm going to say polytope is smooth if the L2 norm of all the WIs is at most tau. That's sufficient for what I'm going to be talking about next. So essentially, they showed the following. They showed that if you take this indicator function wx at most theta, the set of all x's for which wx is at most theta, and the set of all g's for which wg is at most theta, they show that these two indicator functions is at most tau times polylog k. So in some sense, maybe analyzing a polytope is hard in the Boolean space, but maybe analyzing the polytope in the Gaussian space is easy. And maybe analyzing the polytope in the Gaussian space is easy, so we can prove something about the Gaussian space. And so that is sufficient to fool just the Boolean space in the first place. And why Gaussian becomes easy, I will come back to it in the end of the slide. So the first thing is great. So in order to, so for this slide and the next slide, the goal is to establish equation 1. A polytope given a Boolean input is close to a polytope when given Gaussian input. And how do you prove this thing? So it's a 3-step process. So the first step is, right, so they say, I don't know how to analyze this wx at most theta. It's like an indicator function. These things are very, like wx at most theta is like an orthant function. I just don't know how to analyze it. So what they say is, consider a smooth function. Take a function that maps rk to r. And they say, let's try to analyze this expectation value. So again, this is not close to this, but so I'm applying a smooth function to wx. So w is a matrix, x was a bit string, w is a k by n matrix. So w times x is a k or in rk. I'm going to apply just a smooth function to rk. Now, what is the difference between these two quantities? So a smooth function applied to wx and a smooth function applied to wg. What's the difference in these expectation values? The beautiful thing they showed is at most tau times log k times this quantity. And what this quantity means is because it's a smooth function, I can write this Taylor series expansion, look at the third order Taylor series expansion and just sum all the coefficients. I'll come to why they get this in 1 second. Right, so this is a nice result. And the way they prove this is the following. It's using the Lindeberg method or the hybrid method. What they say is sorry,
so a smooth function is one that doesn't strongly depend on any one of its variables. What is it?
Oh, sorry. I'm using smooth. Smooth. Okay, I'll come to what smooth means in a second. Sorry, I'm double using smooth. I didn't realize it myself.
Okay.
Smooth means something else here. It's not like the smooth in the polytope sense. Sorry.
Okay.
In a second, it'll become clear. So what I'm going to do is, because O is a smooth function, I'm going to write down the Taylor series expansion for O because it's well defined. And then I'm going to use the fact that because I'm taking the expectation with respect to the Boolean and expectation with respect to the Gaussian, the first and second moments of these distributions match. So essentially, I'm going to get only the third order derivatives of this smooth function script O. So like because the first and second moments match, I'm going to get only the third order derivatives. And now I'm going to use the fact that the O is smooth. And what that means is like all the derivatives of O are nice and bounded. So all that I'm saying is when I mean smooth function from rk to r, all these derivatives or all these, if you look at the L1 norm of all the first order derivatives, L2 norm of the second order derivatives, all these things are nice. And they claim that all these derivatives are small, so this quantity is small in the first place. So that's what I mean by smooth. I'll again come back to this in the next slide. So that's what I mean by smooth here is very different from what I mean by regularity in this case. I'm sorry for the notation overuse, sorry. Right, so the first thing they show is you can establish a variant of equation 1 by replacing this indicator function by an arbitrary smooth function applied to wx. Right, so the goal is to establish equation 2. We have so far established equation 3. And now is where the beautiful result of Benkus comes in.
So Srini, this statement is true for all functions whose third derivative is small?
Yes. And yeah, exactly. And they're going to instantiate it for one particular O, which is the Benkus modifier. So equation 3 holds true for every O, but end of the day, we need to go from equation 3 to equation 2. So we would like to pick a nice O such that O times Wx is actually close to this indicator function. So you would like a smooth approximation of the orthant function. That's where they invoke this nice, exactly. So we care about this indicator function. Is Wx at most theta or not? We don't care about applying a smooth function on Wx. We only care about whether Wx is at most theta, yes or no. We don't care about an arbitrary smooth function applied to Wx. For that, what they do is they use this result of Benkus back in 90, who said you can actually approximate the orthon function by a smooth function in the following sense. So let's look at the right-hand side. Let's just say I give you a bunch of Z1 to Zk in Rk, and your goal is to tell me whether the max over Z1 to Zk is at most theta or not. So it's a yes or no statement. So it's either 0 or 1 on the right-hand side. But what Benkus showed is there is actually a function for which you can approximate the yes or no function by a smooth function, such that B applied to Z1 to Zk is very close to the max function on Z1 to Zk. And not only that, the beautiful thing is all these, the Taylor series, if you write the Taylor series expansion, the sum of all these coefficients is only polylog in K. Like this is pretty mind-blowing when I saw it for the first time, because if you look at it, like they're firstly, if you just look at just a naive upper bound on this, it's K to the L, because like the first level has K coefficients, second level K square, and so on and so forth. But he shows that there's so many cancellations that are happening in the smooth modifier that you can actually bound the L1 norm of the BL by polylog in K. And as what Harry said, you can so having this the equation 3 works for all modifiers. I'm going to instantiate for the Benkus modifier so that this is equation 3 can be used to upper bound equation 2 also, and that's what is happening here.
EL is the Lth derivative?
Yes. The sum of all, so if I take a function on Rk, I can look at derivatives in different directions. I'm going to take derivatives in all possible L directions, sum all those coefficients. So like B1 would just be the sum of all F1, dF1, dF2, dF3 to dFk. B2 would be dFi, dFj, summation over all j, and maximize over all the inputs. There's still one step that's missing, and this is where the Gaussian picture comes in. So somehow what I've shown so far is this modifier here is close to the indicator function. So B agrees with this, but it's not exactly equal. It's just an approximation. So of course, when going from equation 3 to 2, I should try to take care. There could be points at which B of Z1 to Zk is not even close to this indicator function. So around the boundary of a polytope is where B and O strongly disagree. And what they show, but the crucial idea that they have is, if supposing the mass of the Gaussian sitting in the boundary of a polytope is small in the first place, maybe we don't care. So B agrees with this indicator function on all Z except in the fringe cases of a polytope. But maybe the fringe cases of a polytope in the first place have a small mass in the first place. Like maybe not many x's sit in that boundary in the first place. Is that okay? Is their question? And they proved yes. So what crucially they showed is the Gaussian surface area of a polytope is small. That is, the Gaussian mass of an axis sitting in the boundary of a polytope is small in the first place. And we don't know such a result for Boolean surface area. And this Gaussian result was proven again by another geometric result by Nazarov in 2003, where he showed that the GSA of a k-facet polytope is square root log k. And now if you just put everything together, like 3 implies 2, and if you look at it in the entire, it's like all the dependence is polylog in k. Like this is log k, this is polylog k, this is log k, and this is crucially where going from the Boolean picture to the Gaussian picture helped a lot. You could prove anti-concentration in the Gaussian space, but you don't know how to prove anti-concentration in the Boolean space. And so that's where the invariance principle helps you in the first place.
Srini,
yeah.
Will you say something about how this Benkus modifier is constructed? Because that's where all the magic seems to happen.
True. Yeah, that's where all the magic happens, and we're going to crucially use that magic also in our slide, but I'm not going to be talking about how it's constructed. Like
you're a real magician. You don't show how it works.
Exactly. So, Job, how much time do I have left? Like 15 minutes do I have left, or?
Yeah, you can take 15. Yeah, sure.
Yeah. Hopefully, I'll get through in 15, but I suspect I won't. But let me try. So again, like all this was again the polytope picture, and the thing that Penguin I thought about is let's quantize everything. And what I mean by quantize in the classical sense, let's replace like numbers by matrices. That's really about it. So this is a half space. Replace all these W by matrices, and you can get a spectrahedron, and you would like to understand these things. So the first things first, does the Lindeberg method that was proven in 1922, does it work through for a spectrahedron? And the answer is it's not at all clear, because kind of a spectrahedron deals with eigenvalues of matrices. It doesn't deal with like, I can't replace x1 by g1 and understand this in some sense. because this inequality doesn't make sense when I replace x1 by g1, but I would like to understand how the eigenvalues of xi gi's change when I replace xi with gi. And as far as we know, like we don't know even like if a Lindeberg method for spectral modifiers has been done before. And that's our first main contribution. We show like a version of an invariance principle for just the Benkos modifier. So we can prove a Lindeberg type argument, not just by replacing xi's with gi's, but even talking about eigenvalues of matrices when I replace xi's with gi's. And the second thing is anti-concentration. As I said, like understanding the GSA of a polytope, they crucially use the fact that polytope is nice, it's smooth and everything like that. But a spectrahedron is like a absolutely funky object. Like we don't even know how it behaves in the first place. And right, and you require anti-concentration to go from modifier, Benkos modifier, to the actual CDF closeness. And we don't know, right? And so the second main contribution is we prove it. So like there's this theorem by Littlewood and Alford back in 1943. They proved it for a single half space. It was later improved by Erdash in 45, and then like O'Donnell, Servedio and Tan improved it for polytopes, and we proved a version of Littlewood offered for a spectrahedron now, which talks about eigenvalues of matrices, and that is required for anti-concentration. Right, so let me try to sketch these two things, and hopefully I get through it. Good. So I need, right, two definitions first, and yeah, these are fairly standard, I would think. So what's a spectral function? It's just a function that acts on matrices and outputs a real number. But not only is it an arbitrary function, it acts only on the eigenvalues of matrices. So recall the reason I do this is because like a spectrahedron has this loner ordering. So end of the day, I just care about B minus the left-hand side being positive semidefinite, or all the eigenvalues have to be greater than 0. So a spectral function is a function on matrices that acts only on the eigenvalues of matrices. And simple examples include determinant, traces, matrix norms, shatter norms, everything. And the second thing I need is derivative of matrix value functions, because I'm going to mimic what Harsha-Kleiman's Meka do by looking at a modifier and then writing out like they wrote a Taylor series expansion out, but now I'm going to be acting on matrices, so I can't just write a Taylor series expansion. I need something slightly more. So for that, let's first understand what the Taylor series does. You have a function h from reals to reals. And if I want to write the Taylor series expansion, I can write it around every a as h of x is h of a times the derivative of the function at a times x minus a and so on and so forth. This is just standard, nothing fancy here. And the definition of h prime of a, or the derivative of h at the point a, is just this limit. So this all works for R to R, but I care about Rn to R, like matrices to matrices now. So there's something called Frechet derivatives. And these are just derivatives in Banach spaces. So, so this is, in a way, I would think this is just like standard calculus, but you would like to uptake derivatives of matrices and so on and so forth. And yeah, like taking the Frechet derivative of matrix A in the direction B is just this quantity. It looks slightly technical, but one thing you should observe is this dfab is very similar to what's happening to standard derivatives. You're evaluating the function on A plus xp minus f of A divided by s and taking the limit. But things are a lot more technical here because you're taking limits and you have to be careful about a lot of like continuity and like non-commutativity and so on and so forth. And these things are very hard to compute, like several basic properties, whether when is the pressure there, like whether continuity implies differentiability, what is the Lipschitz continuity, differentiability of all these things in the Frechet world was only proven like some results were only proven like I think 5 to 10 years back. Things that have been known for like centuries in the standard calculus were only proven like very recently in the Frechet world. So these things are pretty hard. Good. So let me try to tell you what is our invariance principle. So we prove the following. This is the quantity we care about, summation xi ai minus b, summation gi ai minus b. And ideally, you would like to apply a function b on the eigenvalues of this matrices. And the main result that we have is you can prove an invariance principle for spectrahedrons only on the Benkos modifier. Unfortunately, our techniques only allow us to prove it on the Benkos modifier, which is good enough, but unfortunately, that's the limitations of our technique. So if you apply the Benkos modifier on the eigenvalues of matrices, then these quantities behave the same if you're in the Boolean field or in the Gaussian field. And the way we establish is through the hybrid method, so the Lindeberg method. For that, what we have to do is some sort of hashing. Like this hashing is important. I'll tell you why in the next slide. So I'm just going to be dividing the sum from 1 to n into like t blocks. And beautifully, I can write what's in the sum because of this hashing as just some term that depends on qx plus p of x times x comma g and qg times p of x comma g. So these two quantities are the same, but the first part is Boolean here and it's Gaussian here. So that's what the hashing buys us. The second thing I'm going to be doing is I'm going to write, because like B was a smooth function on the eigenvalues of matrices, I can write the Fréchet series of it. And I can write the Fréchet series of this and I get this quantity. You don't need to understand this, but you can just think of it like standard Taylor series. It's the value of the function on this point, and then I take a derivative on this, and so on and so forth. So this is the first three orders. So this B lambda corresponds to just this quantity, and I can write the similar thing for this quantity where I just replace qx by qg. That's the only difference. And again, we're going to use the fact that the same color terms are equal when I take the expectation. So if I take an expectation of x, because end of the day, I care only about taking an expectation over x and g, red is same. Is it golden is same, or brown is same, and the blue terms are same. So end of the day, we care only about bounding the third order derivatives. So if we show this, we have shown our main goal and we are happy. But understanding Fréchet derivatives is incredibly hard. This is very hard and we didn't even know how to bound this in the first place. But thankfully there is this result by Sendoff. He's just a pure mathematician. I'm pretty sure he doesn't care what PRGs. He has this nice tensor way to understand Fréchet derivatives for spectral functions. So that's kind of precisely what we need. So that's awesome. So we saw this result by Sendoff in some math journal. We thought, okay, this is perfectly what we need to understand Fréchet series of spectral functions. Great. So recall, the goal is to upper bound prove this inequality right here. Or we need to upper bound this. And again, we want to use the result of Sendoff. He says like you can write down all these quantities nicely. You can write the Fréchet series of spectral functions nicely. But if you write out the Fréchet series derivatives, you're going to get a bunch of standard derivatives. And this is where things become a lot more messy actually. So if you write out the Fréchet series derivatives of matrices, you're going to get like a bunch of 7 terms. The first 3 terms are all diagonal matrices, and you can generalize whatever we have to diagonal matrices and get back the polytope results. And if you dig deep into the result of Ryan O'Donnell, Rocco Servedio, and Tan, all that they do is they bound the first 3 terms in a very clever way. But unfortunately, because we have matrices and there are a lot of non-commutative terms, we have to bound everything from 4 to 7 as well. And that's really where the meat of the technical stuff goes into our work. For the Benkes modifier, for the set of matrices, we are able to bound all these 7 terms by polylog k times the Schatten norm of qg and all these matrices. By the way, this polylog k should not be obvious at all, because if you just look at this term, for example, like I is running from 1 to k, so there are k squared terms. The last one has k cubed terms. So in some sense, you want to bound all these 7 terms only by polylog in k. You cannot do anything naive and upper bounded by just k, for example. Then you've just lost the entire goal in PRGs where you want everything to be polylog in k. So our main technical contribution is you can upper bound all these Fréchet derivatives, third order Fréchet derivatives by polylog in k times the norm of this. And for that, as Harry said, like a true magician, like I'm not going to tell you what the Benkes modifier is, but we have to completely open up this black box. So like the prior works of like Harsha-Kleiman's Meka, OST, Servedio and Tan, many other works, they use Benkes modifier as a black box. Orton function approximated by Benkes modifier. But first, we cannot use it as a black box. We literally have to look at exactly what this function is, and we have to understand what these derivatives are, what's really happening in this construction. And for this particular modifier, we can bound all these terms. So that we have to open up this entire modifier. The last thing that remains to be done is to upper bound all these matrix norms. And even this was not like super clear to us. The reason is the following. So we need to upper bound this in 2 ways. One, like maybe you could use like, for example, a standard like Chernoff bounds or hypercontractivity to bound these things. But we have to use something called the matrix Rosenthal identity for 2 reasons. One, it upper bounds the Schatten norms, which in a very nice way. So it gives you upper bounds on Schatten norms of this matrices. Second thing, we require this matrix Rosenthal to be to hold for p-wise independent distributions. So recall, what is the qx? Qx was summation xi ai. We would like an upper bound on the Schatten norms even for p-wise independent distributions, because that is going to be useful for us constructing our final PRG. So we require 2 quantities in upper bounding qx. One, it gives a good upper bound. 2, it can be it also holds for p-wise independent distributions. And it so happens that we were lucky that matrix Rosenthal just is perfect for us. And as I said, like, yeah, maybe I went through this slide and last slide quickly, but we have the upper bound this, we use send off, we get this, we have one everything on polylog k times the shatter norms of this, and the shatter norms of this can be upper bounded by polylog k, and this pretty much the main gist of everything. Right, and let me tell you maybe a separate, yeah, I think in 5 minutes I can finish. Right, so far I've established an invariance principle. So as I told you, like if you recall Harsha, Klein, and Smeka, they established invariance principles. That was the hard part. But as I said again, just establishing invariance principle was not enough. You need to somehow say that B is close to an orthant function. And in our case, it's slightly different. So far we have established this. And if you just write it, if you stare at this a little bit, this is actually exactly equal to this approximation factor, this approximation thing. And as I said, we care about equation 6 and not equation 5. That is, we know everything in this bracket is close to what we care about, but it's not exactly equal. And this is where the approximation factor and this Gaussian picture comes very handy for us. And what does this approximation thing tell us actually in the first place? It tells us that if all the eigenvalues of this matrix are small, then unfortunately this approximation is not good at all. So the point is, earlier I said if I look at a polytope, if I'm very close to a polytope, then this approximation is not good. But for us, like the closeness to a polytope doesn't make sense. But we want to say if the eigenvalues of these matrices are very close to a fringe or very close to 0, then this Benkus modifier is not a good approximation of our actual spectrahedron function. But if supposing it's far away, then the approximation is good. And okay, right. So, and again, like what people showed earlier for the Gaussian picture, we show also. Oh man, how do we get rid of this? Okay. Yeah. Essentially, what we show is you have a lot of anti-concentration even for matrices. The eigenvalues of matrices cannot be very concentrated around 0. And that's really our main Littlewood-Offer theorem. What we say is if you have a bunch of n positive matrices that are regular in some sense, then the largest eigenvalue, the probability the largest eigenvalue sits in this, remove this grid. Largest eigenvalue sits in a very tiny interval around 0. It's actually very tiny in the first place. And as I said, this was first proven by Littlewood and offered in 43, improved by Erdash. Both of these results were for half spaces. OST improved it for polytopes, and we improve it for spectrahedrons. So in principle, what that means is establishing 8 is sufficient establishing 7 is sufficient, and establishing 8 comes for free because of our Littlewood-Offer theorem. And we are done. Let me conclude. Good. So this was a spectrahedron, was the indicator function of this space. And we constructed a spectrahedron that fools this class with seed length polylog in n, k, but unfortunately depending on m and 1 over delta. What are some open questions? These are pretty straightforward questions. Can we remove regularity? Like this thing that Ronald pointed to the first few slides. All our AIs have to be like kind of small. Like it cannot be like one is super large, one is super small, and so on. Can we remove positivity? So can we fool arbitrary Pseudorandom generator? Sorry, arbitrary spectrahedron, not just positive. So one thing that's a mathematical question is what is the Gaussian surface area of a spectrahedron? For a polytope, Nazarov showed it's square root log k, which is surprising because it's an object in Rn. It has k facets, but the GSA is only square root log k. First, it's independent of n, and secondly, it's only log in the input size. So it's a similar result true for even spectrahedron. We don't know. We suspect it's not small. This is some work that I'm doing. So we suspect that the GSA of spectrahedron is actually large. It's not small like polytopes. So that changes how polytopes are different from spectrahedron. Improve the 1 over delta dependence is nice. And as Harry said, our general invariance principle only works for the Benkus modifier. We would like it to work for arbitrary spectral functions. And we don't know how to establish this so far. The last thing could potentially have implications of quantum, in fact, but yeah, we don't know how to establish it. With that, I thank you for your attention.